I'm happy to introduce and start off our meeting with a presentation by a professor at UMass Amherst in Massachusetts. Brian Yellen is a research professor in the Department of Geosciences at the University of Massachusetts Amherst. His research focuses on watershed processes, especially sediment transport from headwaters to estuaries and erosion due to extreme flooding. Brian is dedicated to making scientific discoveries accessible to stakeholders and decision makers. He leads 2 local watershed organizations and delivers professional development workshops to professional engineers and geologists. And Brian taught high school science before going on to earn his PhD from UMass Amherst.
Okay. Audra, thank you so much for providing the opportunity to speak to this group. And folks who called in, thanks so much for joining. This opening slide is one that folks might be familiar with. This is August 2011, immediately after Hurricane Irene. It's about 4 or 5 days after Hurricane Irene. And what you're looking at is a big plume of classic sediment, mineral sediment coming out of the Connecticut River into Long Island Sound. And a similar plume of water coming out of Thames River over in eastern Connecticut, but of course that one is what we call a blackwater plume, or it's devoid of sediment. There's a variety of things that we've been working on here in the sedimentology lab at UMass. But a few of the big questions we've been asking is, what is the role of extreme events in eroding the landscape, and from a water resources perspective, of course, and then ultimately in training sediment within the water column and in the stream network. We've been doing a lot of work sort of looking at what we might call problem children, or sort of these persistent sources of sediment. It seems that sediment does not come evenly from the landscape, and you can see that dramatically in this picture, whereby the Thames River is discharging a much clearer plume of water. A caveat would be that the impacts of Irene were more felt in western New England, and I think that's part of it, but I think geology plays a role as well. The 2 main points that I'd like to make today is one, that the sort of baseline change in climate in New England, the fact that we're getting wetter year over year, amplifies the effects of extreme events when they do happen. And 2, so basically point number 1 is that antecedent conditions matter. So the fact that we're getting wetter and wetter, just sort of baseline conditions, that amplifies the effects of extreme precip events. And 2, that there are hysteretic impacts from these. And what I mean by that is that when you erode the landscape and open up these sort of wounds on the sides of rivers, small landslides and bank failures, it takes some time for those events to recover from those events. And so as we see more and more extreme events and the impacts of extreme events grow, we would expect to sort of be in a continual process of healing from those events. And you'll see what I mean more as we progress through the slides. So the first thing I'd like to show you are some results from a sediment core in Vermont. This is a representative lake, and we use sediment cores to sort of look back in time at sediment transport. A lot of our observations of suspended sediment in the water column only go back 10, maybe 20 years if we're lucky. They're extremely sporadic, and we can often miss the big events. The great thing about sediment core archives is that a lake or a reservoir, the sediment record there is always listening. It's always receiving sediment. And so here we're looking at a sediment core from the center, sort of south central Vermont, from a lake called Amherst Lake, which is coincidence that I'm at UMass Amherst. And what I've highlighted here are 2 what we call event deposits, so mineral-rich layers laid down in sort of organic mud on the bottom of the lake. And you can see a mineral-rich layer that we've dated to 1927, and I'll spare you the details on how we date it, and a mineral-rich layer at the top, and this is an X-ray of the sediment core, and so that layer at the top represents Hurricane Irene. One thing that's interesting to note about the sediment core is that it was taken about 3 or 4 years after Irene occurred, and so what you notice is that the sediment from Irene continues right up to the surface, i.e. mineral-rich sediment is still being delivered to this lake. And this gets at this idea of these landslide scarps being opened during a big flood and then continuing to weep mineral-rich sediment. But one thing I forgot to point out is that you notice that Irene had a much more impressive event deposit. There was a lot more erosion caused by Hurricane Irene than occurred during 1927. And despite this, 1927 was actually a higher rain, higher discharge event. So there was more rain that fell on central Vermont, and there was more discharge coming out the rivers. Interestingly, and despite that, Irene is the one that caused more erosion. The thing that we've come up with to distinguish these two events and why Irene was so much more erosive is the antecedent precipitation prior to Irene. So in this plot, we're looking at 20 biggest precip events that have occurred in this south central Vermont region. The amount of precip that arrived during that individual event is on the x-axis, and so ranging from about 3 inches or 10 centimeters up to about 8 inches or 7 or 8 inches, 22 centimeters. And then on the y-axis, we're looking at how much rain fell during the month leading up to that event. And what you'll see is there's a lot of events in this space right here. 1927 sticks out as the most rain-rich event, so it's the furthest right. But Irene is both lots of rain and a lot of rain fell in the month prior. So it was the most antecedent precip of all these large rain events. And that was no coincidence, or I should say the likelihood of that happening late in the 20th century or now in the 21st century is much more likely than it was early on when in 1927 when things were just a lot drier. So this last plot on this slide here shows the probability of having had 17.5 centimeters or how many inches that? About 7 inches of rain in the prior month. And what you'll see is back in 1920, there was only about a 2% probability of having had a lot of rain leading up to it on any given day. And so we know that on any given day we can have an extreme event. In 1927, we had big precip events. We continue to have big precip events. We think there'll be more, but it's hard to model that. What's easy to model and what's easy to observe is that there's a general increase in wetness. And we can see here that today we're about 4 times more likely to have had Irene equivalent antecedent precipitation up here at this end of the plot. So antecedent conditions matter, and in New England we're getting wetter. Our chances of having wet antecedent conditions have increased dramatically. Interestingly, most of that increase has happened since about 1970. If you want to read more about this or need to cite this to justify something, this is a publication where you can find more about this work. Another thing I'll point out is, although I'm showing data from southern Vermont, we also show data that encompass all of New England in this paper, but this is just sort of a nice snapshot. The second place I'd like to take you is to the Ashokan Reservoir in upstate New York. This reservoir supplies about 40% of New York City's water. Here we are looking at the west basin and east basin of the Ashokan Reservoir. The west basin here is the one that receives water from the Esopus Creek. And you'll notice some 40 days after Irene, it's still receiving turbid water. So what I'd like to highlight here is that big floods themselves generate a lot of sediment, but they also disturb the watershed and lead to continued sedimentation following the event. And so that's what I'll be talking about with Irene, with Ashokan. To try to predict the amount of sediment that's going to come into a reservoir, we use the sediment discharge rating curve. This is folks who are in the water resources end in this call are probably familiar with this. Here's a plot of discharge on the x-axis and the amount of sediment on the y-axis. The unit for the amount of sediment are turbidity times discharge. So it's a little bit of a weird unit, but the nice thing about using turbidity is we measure it often. On this particular sediment, turbidity and suspended sediment concentrations co-vary almost perfectly. So it's a really nice proxy for sediment. So here you'll notice it's sort of a power law relationship. If we show it in log-log space, or if we log transform the data, we get a nice linear fit. And so here at the top of the screen is the equation for relating discharge to the amount of sediment coming into the reservoir. Don't worry too much about the details of the sediment, just of this relationship. Just recognize that it has an mx plus b form. Here's the slope in blue. There's our m times our our independent variable, which is discharge, and there's our y-intercept, the log of 0.041 for this particular river, the Ashokan Creek. And so by putting it in log space, we can reduce it to this slope and intercept, and you can see the slope there. And what I'd like to show you now is that after big events, we see that y-intercept changes. On this particular system, the slope tends to be relatively constant before and after an event. So here we're looking at discharge on the y-axis, sediment on the sediment on the y-axis, discharge on the x-axis. And what you'll notice is the blue dots are before a big flood, the red dots are after a big flood. And you'll notice that the line gets shifted upwards after the big flood, so that for any given discharge, we would expect more sediment in the days following this 1996 flood. In the case of Tropical Storm Irene in 2011, same thing, same pattern occurs, whereby the y-intercept or the whole line is just shifted upwards. And so what that means in real words is following a big flood, you're going to get more sediment for a given discharge. So even once the discharge relaxes back down to sort of what you'd expect, more normal discharge conditions, you're getting excess sediment on the order of sometimes 2 to 3 times more sediment for a given discharge level. Again, here's the form of that log transformed sediment discharge rating curve. And what here, this beta naught term is the y-intercept. And so we can represent the increase in sediment for a given discharge by the shifting of beta naught. What we're looking at here now is looking at the beta naught term, or the y-intercept of the sediment discharge rating curve, going back to the beginning of the turbidity record on Ashokan Creek, which feeds into Ashokan Reservoir. And what you'll see is that there's a series, each of these brown dashed lines represents a big flood. And each time there's a big flood, I'm not animating anymore, each time there's a big flood, you'll see that there's a dramatic increase in beta naught. It shifts the sediment discharge rating curve upwards, and then it relaxes back over the next few years. With increased frequency of extreme events, and also with an increased impact of extreme events when they do occur, because the ground's just generally getting soggier, we expect this impact to be greater and greater. So managing sources of sediment from upwards and uplands within our drinking water watersheds is going to be really important moving forward. Not that folks are not already sort of thinking about that. Again, if you want to look to see more information about this, here's the citation down in the lower corner. So the third point I'll make, and this is getting toward the end of the presentation now, looking at Ashokan Reservoir, also collected sediment cores from this reservoir. And again, the great value of sediment cores is we can look back now to when the reservoir was built to see how has the relationship between discharge and sediment delivery changed over time. On the x-axis here, we're looking at time going back to 1950. On the y-axis, we're looking at the amount of sediment delivered for individual flood events. Each of these red dots represents a historical flood going back to about early 1950s. The size of the circle is the amount of discharge, that the peak discharge for that flood. And so you'll notice that the size of the circle varies, and that means we've had different size floods that have brought event deposits to the reservoir. What you'll notice, though, is there is a general increase in the amount of sediment delivered for a given flood, even though the floods are not generally getting larger, with the exception of Hurricane Irene, which is sort of the outlier. This is Hurricane Irene, the most recent one. But you can see, even early in the record, some of these more moderate flood events, like this one in 2006, was the most sediment-rich flood prior to Irene. And then, of course, Irene came along as an even bigger flood with more sediment. What I really like to highlight is that you can see the impact of this general wetting condition, getting wetter and wetter in New England, and as a result, our large floods, even these sort of on the order of 5 to 20 year flood occurrence intervals, they're generating more and more sediment through time. So, in conclusion, a baseline wetter climate is amplifying the effects of extreme precipitation. And so our climate's getting wetter, and we should expect when we do get big rain events that their impacts will be stronger. There's a hysteretic response of rivers following erosion that shifts the sediment discharge rating curve upwards. And then 3, and I think this folks who in the webinar are well aware of this, but in the Northeast, there's a projection for us to continue getting wetter And so we should be planning for these conditions. If you need to contact me, here's my contact information. And I do want to point out that a lot of this work was done with the help of collaborators. And so I'm sort of representing the UMass group here, but certainly this is not exclusively my work. And with that, I'd like to stop and ask what questions folks have.
Yeah, so feel free to speak up if you have a question. We'll make this pretty casual. Brian, this is Audra. I'd like to ask if I'm a watershed manager or someone in my local area and you've just given me this information, what would you recommend that I'm doing to help better plan for the increased sediment? I mean, I think we've heard a lot about the increased precipitation and certainly are aware of the more extreme events, but from the sedimentation aspect, what kinds of things should we be more attuned to because of this?
I mean, I think I'm not a water resource planner, but, to the extent that I can speak to that would be, planning alternate sources of water supplies for these extreme events to allow sediment to settle. I think establishing what are some of the background deposition rates in your reservoirs is something that's relatively easy and inexpensive to do. Just to know sort of how quickly the reservoir is filling up and compare that to ongoing rates. And then in terms of sort of within your watershed, to start thinking about sediment mitigation projects. One thing I should point out is that the majority of sediment in the Northeast, in our post-glacial and steep environment of the Northeast, the majority of sediment comes from erosion of glacial material along the banks of our rivers. It's not coming from rill erosion or gully formation. It's not a broad landscape process happening across hill slopes. It's really focused along the banks of our stream. And so during these high stream power events, that's when we get sediment addition to our reservoirs. So to the extent you can mitigate sources of sediment, I think if I were planning doing watershed management activities, I would really focus on stream side stuff more than broad landscape scale stuff.
Yeah, okay, thanks. That makes sense. Other people have questions for Brian?
Hi, Brian. This is Kristen. I just had a question. Do you have examples of these mitigation projects that have shown reduced erosion rates?
Great question. So I'm not a stream restoration practitioner, but I have been working with the New York City group. One of their big concerns is this Ashokan Reservoir, which I'm showing some figures from. They have been doing a lot of stream turbidity mitigation projects. Forget their acronym. Anyhow, so everything from installing sheet pile into the bed of streams. So basically, sheet metal, driving it down to put it on grade with the base of the stream, such that to minimize down cutting. They're having a lot of issues with streams that are down cutting into glacial sediment. And then another thing that they've been working on is where water is being added to stream banks from above, where there are streams coming in from above. Often there are beaver impoundments 10, 20, 30 feet above the stream that are moistening the banks, trying to move that water away from these tall banks of glacial sediment, whether it's glacial till or glacial lacustrine sediment, trying to dry them out by routing water away from them. They're in the midst of undergoing a really intensive review process to try to evaluate, has all this work been worthwhile? Unfortunately, the conclusions of that report are not going to be due out until next spring, being done by the National Academy of Science, an independent review panel. Definitely, Danny Davis is the person I've been working with there, and if folks know folks at New York City, she sort of runs the Ashokan Watershed Management Program. And so talking to her, I think, would be, if you're looking for a resource, he's sort of on the front lines of doing this work.
Great, thank you.
We have just a few more minutes if anybody else has a question for Brian.
Brian, this is just kind of a general question, but are there people across New England looking into this in terms of the amount of sediment and then ramifications of that sediment in terms of drinking water or natural resources?
Yes, that's a good question. So sort of more on the engineering side, I can't speak to that. There should be.
Yeah.
And in terms of natural resources, you mean sort of like ecosystem services and impacts to downstream ecology?
Yeah, biology and, just fisheries resources and or, other natural resources that we depend on and their impact that we're just not thinking about in terms of, long-term effect. And is this something it sounds like it's something we need to seriously start thinking about and addressing.
Yeah, I mean, and part of my motivation, and I've reached out to Audra, was to foster these discussions. And if you know folks who are working on that, we're excited to work with them. And so the UMass Sedimentology group, it's a pretty big group, and we have a lot of resources available. So as we're able to help, we'd love to. I will mention that one sort of ecologically sensitive area that we're doing a lot of work on is within salt marshes. I know some folks in the group are in coastal resiliency. Our group's been doing a lot of work on sort of what are the sources of sediment available to tidal marshes, both in freshwater estuaries, in freshwater tidal settings, and along the coast. I didn't present any of that work. I didn't realize we'd have coastal folks, but that is sort of the one sort of more ecological site we're working in. But certainly ramifications and implications for ecology is certainly not something that is directly in the center of what we do, but certainly motivates us.
Okay, thank you.
Great. Well, thank you again, Brian, for presenting today.
Yeah, thank you, Audra. And I'll just say we're interested in breaking down the walls between the folks on the front lines and the academics. So really want to broaden the impacts of our research. And anytime you think we might be able to help, feel free to give us a call.